All right. Good morning, all. We will continue our journey through generative AI. And when I gave this lecture 2 years ago, the best image generator there was were diffusion-based models, and the theoretically more well-founded flow-based models could not yet do the trick. But that has changed since. And Peter pointed out this paper to me. He went to ICML this year, and this is where this paper was presented. And they use flow-based methodology to achieve state-of-the-art image synthesis. And so I was very happy to see that, in particular, that diffusion models can spell now, because when you create images and you tell them, the image should contain a label that says something, that's something that frequently still goes wrong, and the fact that this specific model can spell now is nothing to do with diffusion model versus flow-based. It just says they have managed to come up with a really well-working pipeline. And there are in the appendix many pretty images of pretzel-shaped spaceships, augurs with pearl earrings, whatever, plenty of distraction. So very, very high quality image synthesis that is now possible with flow-based methods. And I highlighted here Patrick Esser and Robin Rombach. Robin studied physics here. Patrick, I'm not sure what he studied, but both did their PhD with Björn Ommer when Björn Ommer was at IWR here at Heidelberg University, and they later moved to Munich. And then Patrick and Robin and many others joined Stability AI, and they've since founded their own company, which is the Black Forest Labs. And there's also Tim Dockhorn here, by the way, who was here to give a talk in the IWR colloquium, very nice talk on diffusion-based models 2 years ago. Okay, so the bottom line here is that flow-based models, they no longer are just beautiful for theoreticians, but they start to work well in practice. And we were discussing, so we continue today with flow-based models. And there are very many of them, and it's many names to know by heart. So the class as a whole doesn't have a really nice name yet. This is why I write flow-based models here. They are sometimes called normalizers. And the reason is that we were looking last time at the setup where we have a base distribution, and this is something that we can typically sample from easily. And I was saying that this here lives in a space called Z, and then we have a target distribution. And today I'm going to make our lives exceptionally simple, and I'm going to also use a normal distribution here for the target. And we were discussing last time the QQ plot, so how I can find quantiles here and how I can then map these quantiles to each other. And so on. Yeah, and so if I map a normal distribution to a normal distribution, all I need is the identity function. But that's, of course, not the only mapping I can achieve. I could also, so, you know, any bijection works. So I could also use this one here. Or we could do something more adventurous. We could start here and then continue here and then continue there and go on here, or many others. Yeah, so these three, we can look at them in a bit more detail in a different picture. So I'm plotting my base distribution. And I'm plotting my target distribution. And well, the simplest solution of going from base distribution to target distribution is by just using the identity. And I've here tried to reflect somehow the density of quantiles. So that's the white solution that we've seen along the diagonal. But there's the green solution. The green one, okay, I'm going to use a new plot. I'm not drawing the distributions each time because they're the same. So the green one flips it, right? It goes here, there. The only point that doesn't move is the one right in the middle. And that's also a bijection. It's one possible means of turning my base distribution into the target distribution. Let's look at the red one. What does it do? It's an identity mapping initially. And then the second quartile moves to the third, but without inversion. So this one goes here, that goes there. So it looks roughly like so. And vice versa. And then in the final part, so this was part 1, part 2, part 3. In the final part, I again have an identity mapping here. And we can look a little bit at the properties of these. So we can ask, are all of those bijections? Is it a bijection? So is it a one-to-one mapping, one-to-one and onto? And the first one, yes, it's a bijection, and the second one also, and the third one also. I can ask, but is it a smooth map with a smooth inverse? Is it a diffeomorphism? The first one, yes, it's a smooth map with a smooth inverse. The second one actually also. The third one, no. So here, this, as I move along this direction, here there's already a first jump. The jump is especially crass here. This point gets mapped here. If I move a little bit further, the next point gets mapped there. So no, this is not a smooth map. It's not a diffeomorphism. So diffeomorphism, if you want the physical analogy, so if I take a piece of cloth, and so as long as I don't fold it, yeah, so whenever I do this, those are diffeomorphisms. Yeah? But as soon as I fold it over, it no longer is. All right. Then I can ask, so, you know, bijection, we could argue that all are equally valid, but most of us will, you know, least prefer this solution because it's a little bit complicated, and we might prefer the first one over the second because I would argue it's still less complicated. And how would we argue this? Well, we could, for example, argue in the sense of how much, if we look at it as a dynamical system, how much kinetic energy is in the system. So let's say I consider 2 points here, and they are now moving over time. I parameterize time from 0 to 1, and I can ask what's the kinetic energy of you know, this whole set of particles. Now I can ask the same question here. I can take these 2 particles and ask about their kinetic energy. All right, I should invert. And well, we have one particle that moves as fast on the left-hand side, but we have one that needs to move faster because it moves diagonally. And this dynamic picture, or asking what's the kinetic energy of flowing the one probability mass into the other, this is one formulation of optimal transport, at least if we use the quadratic Euclidean norm as a cost. And so we can ask, is it optimal transport? The first one is, and this one is not, and that one is not. All right, but since we already talk about particles and trajectories and so on, we could come up with even more adventurous solutions. We could say, you know, let's have some kind of flow, let's make it smooth. And it does give, what I am drawing here, does in fact give the identity mapping. It's, you know, it has nice smoothness properties, but it does something more complicated in between. And so, you know, this is a valid mapping from one probability distribution to the other. So what's different is that, well, here we have straight lines. Meaning, in principle, rather than integrating, even in such a case, rather than integrating a pretty boring trajectory, all I need to know is where is it heading, and then I can jump in from beginning to end in a single step. So straight lines, question mark, yes, 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 and no. And let's complete the table. Is it a bijection? Yes, it is. Is it a diffeomorphism? Yes, it is. Is it optimal transport? No. Does it use straight lines? No. So here, because it doesn't use straight lines, multiple integration steps are needed. And this kind of model is actually used in the real world. This would be an example of a neural ODE, a neural ordinary differential equation, and I'll say a little bit more about that later. And then there's even more formulations of how to turn one probability mass into another. Namely, I could also say I'm looking not at an ordinary, but at a stochastic differential equation. So I'm starting here, and then I have some kind of diffusion process. And it might end up in the very same place that the ODE would have taken it, but starting at the same point, a different realization may also end up elsewhere. So for this stochastic differential equation here, is it a bijection? No. Is it a diffeomorphism? Yeah, it can be. Is it optimal transport? Certainly not. And straight lines? Certainly not. So on the right-hand side are models which are more costly at inference time. So on this blackboard here, we can say that multiple passes through my neural network that I will use to perform the mapping are required. But that in turn gives me quite a bit of modeling power. And here, in principle, I can create samples. I can synthesize samples in a single step with all of these models here. And those were the main use cases after all. So we had the main use cases of these flow-based models are, on the one hand, the forward mode, or synthesis when we want to create new samples, for example, new pretty pictures. And there is the inverse mode, or the inverse mapping, where we compute the probability of a given sample. And that, as discussed last time, is important for outlier detection and so on, because I can train a kind of flow-based model on, for example, old physics, and then I can perform real measurements with my real collider. And if I then find new samples which under the inverse mapping are found to have very low probability, then I can ask myself, was my training set not good enough, or did I discover new physics? So this is interesting for outlier detection. All right, so there are all of these possible mappings. So here, what I plotted were what I've shown here so far, here the white mapping and the red one and also the green one. All of these, they were concrete maps. So those were deterministic maps. Deterministic transport maps. Where each point from a base distribution gets mapped to a single point from my target distribution. But I can also have couplings instead. So, these are, well, curves in space. and I can also have more complicated couplings. For example, an uninformative coupling would be this one here. That would be a very bad coupling. But those are distributions which have the correct marginals. Yeah? So it has, if I integrate out one dimension, it's found to match the target distribution. If I integrate out the other dimension, it's found to match the base distribution. And these couplings are normally evaluated by how far they deviate from the diagonal. So how far I move mass. What this means is that any single point, like this point here, it does not get mapped to a single point on the target distribution. Rather, I have a distribution of where it gets mapped, or with which probability it gets mapped to which other point in the target distribution. In this example, it looks like this must be inferior, but there are cases like when I have, in discrete distributions, when I have one unit of mass here and I want to match it to the 2 half units of masses elsewhere, then I must transport a little bit of the mass here and a little bit of the mass there. Yeah, and this I can only do with such couplings. So we have this huge space of possibility. Yeah? We have an infinite number of possible maps, and we have an infinite number of possible couplings, some better and some worse. And today is about what strategies has the machine learning community come up with to find reasonable maps and reasonable couplings. And so we will discuss mainly 2 classes of models. In the first class of models, I want to talk about our coupling flows. Last time, when we painted this picture here, and it was a bit a more complicated one where the target distribution was not quite as simplistic, we were already discussing, as I stretch or compress my base distribution, how do I need to correct for this stretching when I compute the probability at the target distribution or vice versa. And we wrote a formula as follows. So the distribution over my target variable x, its probability density is given by the distribution of my base variable. And then we were correcting, we were looking at the slope of this mapping. And we were taking the absolute value and arguing that when we stretch the distribution and we get a big slope, and so this is why we took the inverse here. And this was in the one-dimensional case. And in fact, this very same formula, we can write letter by letter the same thing. This is the multivariate generalization of what we had last time. This here is the Jacobian. So my flow now is a flow field. I have several dimensions, z. So I'm now moving to more interesting scenarios where my target distribution is no longer one-dimensional, but it lives in a p-dimensional space. And so here I have the Jacobian, and the bars here are no longer absolute value, but these bars now represent the determinant. But otherwise, the formula looks exactly the same as the one we had last time. And in coupling flows, the way we can train them is by maximizing the likelihood of our training samples. So given some base distribution that we can pick ourselves, and normally it's the normal distribution, and given an observed set of samples, what we can do is maximize the likelihood of these samples under the transformation. And this transformation F is we're going to instantiate this as a neural network. So this is a neural network with some parameters, let's say theta. So we maximize the likelihood, or we minimize the log likelihood. All right, and so in this formula here, so if I want to okay, so I'm going to get the likelihood, I'm taking or to minimize the log likelihood, I'm summing here over all of my samples, and we are interested in what probability they have given the parameters theta of the model. And then we are minimizing this with respect to the parameters. And this will give me my optimal transformation. Now, if I use this formula, there's something about Z here, but I need to know which Z a particular X corresponds to. So I can use the fact that I have an invertible mapping. So I'm writing PZ, and now I'm replacing Z by the inverse value or the inverse function of X. And then the Fz by dz is also distributed at the value z equals f to the minus 1 x of theta. Okay. So formally, if I had a single layer neural network, then this would now be my loss function, the negative log likelihood, and I would minimize it with respect to the parameters in the neural network. All right, any questions so far? Yes. Yes. You are totally right. This was wrong. Thank you. I would say it's, if I look where samples end up, given sample may end up in different positions. So I would say it doesn't make sense to talk about this being differentiable. I mainly wanted to bring it into the same kind of format. Yes? What did I say? Well, but what does it, where does this point go in expectation? In expectation, the only thing that we can say is that we map one distribution to the other, but I don't think that the expectation of where this particular sample goes is anything meaningful. I could be wrong, but that's what I think so far. Yeah, it's not like 50-50. It can really go anywhere. If I start many realizations, I can end up on any point down here, and I'm not convinced. So I think what even will happen is that, in principle, under an infinite number of realizations, I think I will obtain the complete target distribution by always starting from this point here. I think from any point, if we do infinite realizations, we always get the same distribution. Yeah. So now, okay, in practice, you are right. In practice, if I start with a single seed, if I throw my noise dice multiple times, so if I use the same prompt and the same seed, and I just use different noise realizations, I typically end up with similar looking pictures. Yeah, like it might be the superhero who either looks right or left, maybe. But I think this has to do with the fact that we don't use in real implementations an infinite number of steps, so not a perfect noise process, but we do mainly maybe 20 iterations or so. And then in practice, it is like you say, if I now move through the space of seeds, I create similar looking outputs. That's correct. But I think this is to do with the fact that we discretize this space fairly coarsely. Yes? These curved lines here, I wanted to indicate some flow field which preserves the probability mass. And I just wanted to emphasize that, yes, these straight flows are possible, but this is only a tiny subset of this much broader family of arbitrary probability preserving flows. Yes, you could. And then we are in this world of optimal transport-based flow algorithms. All right, any more comments? Good. Then we have this beautiful formula here. But so far, this is for a single layer network. And in practice, we are going to use deep networks here. And what we see here is that we always need to be able to invert the entire network. This is the crucial requirement. And a deep network is a composition. So if we say that X is some function of our starting point Z, and it has parameters theta, then in multilayer perceptrons we have a composition. So we have layer capital L, which depends on the output of the layer L-1, which depends on the output of the previous layer, and so on. Somewhere at the very beginning, we have a first layer that accepted the input X. And now each layer has its own set of parameters. I'm missing a couple of dots here. So this is parameterized by theta L-1, and this is parameterized by theta L. Okay, sorry for the squeezing here. Good, this is the forward direction, and this is overall invertible. If each layer itself is invertible. So Z, which we've normally written as f to the -1 of X with parameters theta. And now I proceed the other way. I invert the first layer, and then I invert the second layer. I invert the Lth layer. And now the Jacobian of this entire thing here, this Jacobian of the composition, can be found by the chain rule. And the absolute determinant of it, the absolute determinant is, so the absolute determinant of a product is the product of the absolute determinants. And product of the, I mean, I don't need absolute here. So the determinant of the product is the product of the determinants. Okay, and now, as a last thing before the break, we will look at the first architecture, also historically the first kind of architecture to implement that kind of invertible mapping, and that was real NVP. and the way this works is that we need multiple dimensions, and now we split our dimensions. So we have some base dimensions is ZA. So this entire thing was my latent vector Z, and I'm splitting it into two parts, ZA and ZB, and I'm just trying to indicate here, this would be the whole vector, this would be the first few dimensions, and this would be the second few dimensions. So we have a concatenation here. And I'm now using a kind of flow diagram to map this to XA and XB. And these first few dimensions, they are unchanged. But the second few dimensions, they are manipulated. Namely, they are multiplied pointwise. If these vectors here have the same, okay, they are multiplied pointwise by a scale by some number, which is by some positive number, which is a function of the first few dimensions. So we can have here as the output of this, this is often modeled as e to the power of, this is to make it non-negative, some neural network of ZA. So here we have multiplied with some non-negative number, and then we can add to it. So this was my neural network 1, and I can have a second neural network. Sorry, this is a bit small for people in the back, where we add element-wise some constant. So the first part here is unchanged. And the second part is an invertible function of the input. And it's invertible because if we now go back, we know that XA and ZA is the same. So I can reconstruct on the forward path what was the input to this neural network. And I get out a number. And this number, well, if I previously added it, I can now subtract it. And here I multiply it with some number. So this time I can recompute what this number would be, and I can divide by it. And I obtain my input ZB. So this is, and I can now stack this across multiple layers. So it's deep and it's invertible, but it's also a kind of constraint. It's a kind of weird architecture. Yeah. So it's deep and invertible, but weird. It's let's say it's quite constrained. The fact that this here is made a positive number, by the way, is to avoid flippings as we had here. So we always multiply with some positive number to stretch or compress, but we don't want to flip. This is why we make this a positive number, and this is why the exponential is used here. But any other function that guarantees positivity could also have been used, like the ReLU, for example. Okay, and now this was, so here the second set of dimensions was influenced by the first. Then one can do the opposite. One can now modify the first set of dimensions based on the second, and then overall one has obtained a transformation of the input, which is invertible, and this the parameters in this network can then be found by minimizing the log likelihood here. And in that way, we have found some mapping, but by no means, the perfect mapping, by no means the optimal transport mapping, but we have obtained some mapping that takes us from the base distribution to the target distribution. And this was the first family of architectures from, what was it, 2015. 2015. And after the break, we can look at more recent, more modern architectures to give us good mappings from base to target distribution. We have a break until shortly past 10.